In this video, I want to talk a little bit more about combinational logic design in SystemVerilog. So just like with uh, state elements that we saw for flip-flop and latch, in which we used always a statement, we can use a similar concept with combinational logic circuits too. And in addition, we can use if and else statement and also case and case Z statements too. So if and else statement, you saw one example before in the design of a resettable flip-flop. So now I want to show some examples in the combinational logic context. So let's just re-implement one of the first SystemVerilog modules that we had before. If you remember, we had this gates module that we defined at an earlier video, in which we had two inputs A and B, each having 4 bits, and we had 5 outputs, again each having 4 bits, and each one was basically the result of bitwise operation of A and B. So Y1 was AND of A and B, Y2 was OR, Y3 was XOR, Y4 was NAND, and Y5 was NOR. So here I want to do the same implementation, but instead of using the assign statement, now I want to use always comb. So this is a keyword that is being used when you want to define combinational logic circuit using always statements. However, similar to what we had for the always latch, there is no sensitivity list here. So here what we have is we have always come, and then following that we should have a statement that says what should be implemented. But since we want to implement 5 different functions, so it is more than one statement, we put them between a begin and end, and that way SystemVerilog knows that all of these are basically the statements that are dependent on the always come. So now between begin and end we can specify the functions that we want, and as you can see, there is no need to use assign a statement at the beginning of each line. So this way of implementing functions is usually preferred when we are implementing more complex functions. For this very example, it is not necessary because the function is very small to begin with, right? So you could have just implemented using assign statement in fewer lines of code rather than including them inside always come begin and end, right? But this is a different way of implementing the same function, but now using always statements. But there are other cases that this becomes useful. So for example, let's say we want to create a 7-segment circuit. So you remember from a previous video when we talked about how we can come up with the Boolean functions of a 7-segment display. We had a 4 input data or 4-bit data, and we use that to find out which one of these LEDs should be on to be able to represent that number associated with that data input. So for doing that, one way is to coming up with all the Boolean functions and then implement them in different modules or in a single module, but that is going to be very cumbersome. Why not put the whole truth table inside the module itself, right? So anytime one data appears as input, you know what you should put for the output. And that's exactly what we wanted to do here. So we have created the module. So you see we have module end module. We named it 7-segment. As for the input, we have input with the type logic, and it's called data, and it has 4 bits. And for the output, we have segments. Again, they are of the type logic, and they have 7 bits, right? So each one of these is associated with one of these LEDs here. Now what we can do is that we can use a case statement to check which one of the data or which one of the rows in the truth table happen. So we have always come. Remember, case statement need to be always inside always statements. And then we have case data. So that means that anytime a new data comes, this case function checks it to see what is its value, and for all the possible cases that can happen, you have a set of outputs. So if the data value is 0, then you have colon. That makes the segment to be equal to 1, 1, 1, 1, 1, 1, 0. So if you remember, we had A, B, C, D, E, F, and G. So the 7 bits of the output segments are basically ordered like this: A, B, C, D, E, F, G. So when the data is 0, what happens is that LEDs A, B, C, D, E, F are going to be on. So when we have A, B, C, D, E, F on and G off, that's basically 0. Let's say for another one, if the data is 5, the output is going to be 1, 0, 1, 1, 0, 1, 1. So basically A, F, G, C, D are going to be on, while B and E are off, right? So basically what we did was that we copied the complete truth table inside of our module. So there is no need for coming up with the Boolean equations and then maybe simplifications, right? Anytime one of these data happens, the output is readily prepared. Of course, we don't have to even care about the amount of delays too, right? Because if we actually implement this truth table using basic gates, then there might be some delays between some of the inputs to the outputs, because they have to go through different gates. But this one, the delays for all of the outputs is going to be the same. One thing that you should consider is that we have all the cases for the data from 0 to 9, and then we have a default case which specifies what we should do if the data is greater than 9. So if you remember, when I was talking about 7-segment display, we said that there are some possibilities. One was that for all the values greater than 9, the LEDs are off. One other option was for all the values that are greater than 9, you show the hexadecimal equivalent, right? So this one clearly only shows the values that are between 0 and 9, and for all the values that are greater than 9, you set the outputs to be all 0, so all the LEDs are going to be off. But one thing that you should consider is that for using the case statement, you should have all the possible cases listed. So when we have a 4 input data, in total we have a 4-bit data, in total we have 16 possible combinations. So since I only specified 10 of them, the rest should be specified using a default, right? Otherwise, some unintended consequences might happen. More specifically, let's say you don't have this line and then you give a data that is greater than 9, right? So since there is no case for that specific number, what happens is that this output remains at its previous value. So that's one of the examples that you have some memory functionality without you wanted to have it, right? So it is important that inside case statement you always have all the possible cases. So if there are cases that you don't care about, you still have to provide a default case that basically anything outside the specified cases fall under that category. So case statement imply combinational logic circuit only if all possible input combinations are described. If there are some combinations that are not specified and those combinations happen, that means that the output is going to be the same as the previous output. So it remains at its previous value, and that kind of negates the concept of combinational logic circuit. So you should always remember to have a default statement if there are some cases that you didn't take into account. But what if we want to have some cases with don't cares? So let's say with regard to the priority circuit that we talked about before, there are some rows or there are some variables that are don't cares for some combination. If we don't want to include all the possible combinations, there should be a better way. And that's actually what we have here. Instead of case statement, we can use a case Z or cases statement. Just keep that in mind. We have cases. And this allows us to use don't cares as well. To represent don't cares, instead of the values, we can use question mark. So that means that whenever the input data A is 1xxx, or basically if the first or the most significant bit is 1, the value for other bits don't matter, put the output y as 1 0 0 0. This is for the second case, this one is for the third one, the last one, and then finally we have this default case too, that if we consider this default case is going to be when A is 0 0 0 0. So we could have just spelled it out as 0 0 0 0, or we just put it as default case. So cases and case statements are very powerful tools, so we can basically completely copy a truth table inside a module without the need to actually come up with the Boolean equations for that module. So now we have seen several ways of assigning a value to a variable. So when we were working with flip-flop, we saw this sign basically, which was representing an arrow. So we said that Q, for example, gets the value of D. Also, when we wanted to work with combinational logic circuit, we used only a equal sign. So there is a difference between these two and when they are preferred to be used. The first one is what is called as a non-blocking assignment. And this is being used when there are multiple assignments that need to be done simultaneously. On the other hand, this one, only a single equal sign, is called the blocking assignment. And for this one, you only need to use them when you have a sequence of assignments that need to be done one by one, right? So let's just take a look at the module for a synchronizer, one with using a blocking assignment and the other one with non-blocking assignment. So the one with the blocking assignment is to the right, the one with the non-blocking is to the left. So we have the usual ones: module, end module, the name, the inputs. If you remember, for the synchronizer, we had one clock input, one data, and one Q. So the sets of the inputs was the same as a single flip-flop. But what was different was that we actually had two flip-flops back to back. So that's why we have defined this internal node. And then what we have is, we say always FF. So we define a flip-flop, and at the positive edge of the clock, what we do is that we execute these two lines. If you remember, for the design of the synchronizer, we basically had a flip-flop here another flip-flop like this. They both were getting the same clock signal. And then we had this data, which was asynchronous, and we want to avoid any metastability. So this one was acting as a buffer, and on the rising edge of the clock, what was happening was that the new data would be stored here, and the previous data of this one would be stored here, right? So since both of them getting the exact same clock, the operation of this flip-flop and this one is simultaneous. But if we put it like this, we just say n1 equals d. Basically the value of d is assigned to n1 and the value of n1 is assigned to q. When we do the synthesis, this is basically what we get. As you can see, this is simply a d flip-flop. What is only changed is that we have one internal variable that what it does is basically store the value of d in n1 and then pass it to q, right? So this is not the functionality that we intended. We want to have two flip-flops back to back. And the reason that this happens is that we are using blocking assignment. So when we are using blocking assignment between these two lines, it basically tells SystemVerilog that first execute this part and then execute this part. While for the synchronizer example, as soon as the edge of the clock happens, these two work simultaneously. So that's why we need to use non-blocking assignment to have the functionality that we want for the synchronizer. So what is changed in this implementation versus this one is that now we are using non-blocking assignment instead of blocking assignment. So on the rising edge of the clock, n1 gets the value of d and q gets the value of n1. So when we synthesize this circuit, this is actually what we get. We have two flip-flops connected back to back. One is being used to act as a buffer, and then the next one would get the input of the first one, but only with one rising the edge of the clock difference, time difference. But the whole point was that using this design, we were able to reduce the probability of metastable state for our flip-flop significantly. So you always need to pay attention which one of these two types of assignment you're using. So whenever you're designing a synchronous sequential logic circuit, you use always FF, and you always use non-blocking assignment. Whenever you're designing a very simple combinational logic circuit, you use what is called as the continuous assignment. Remember, with the keyword assign. And whenever you are using more complicated combinational logic circuit, you use always com, and then you use blocking assignment.